Should we start? Yeah, let's start. We should. Okay, so I have some things to talk to you about. MP1 and Homework 0 are available and due Friday. Homework 0, whoa. Do not bring it to class. That whole thing, I think it's probably on the website somewhere. That's just wrong. Ooh. So do not bring to class. The thing we're going to be grading is the part that you submit to the Subversion repository, and we're going to expect to see a PDF there. So don't just leave us your LaTeX. We're not picky about what that PDF looks like, but that's certainly what we care about existing. Well, except that we hope it has all the right answers. All right. So we were a little surprised to discover that our first exam is next week, like starting Sunday. It's available for you to sign up right now, and the material on it goes all the way up through Friday. So it's intended that, you know, these exams are kind of just in time. As such, we're not going to do review sessions. They're not intended to be long and awful. They're intended to just kind of be a motivation for you to stay on top of the stuff. Now, this very first one is kind of an experiment for us as well as for you, I'm sure, because while we've been using the testing center for this is our third semester now, I still haven't really liked exactly how it's gone. So this is yet another chance for us to try and fine-tune the mechanism for assessing how much you're learning, particularly in your coding skills. So to that end, this first one is going to be like a, are you listening? However, it does include the material from MP1. So you can use that kind of as a guideline, Lab 1 and MP1, as a guideline for the kind of code that we might expect you to write. If I were you, I would be wondering if we were going to ask you to write a makefile. What do you hope the answer is to that? No, yeah, okay, right. No. So the answer I can affirmatively give is that we will not ask you to write a makefile. We may ask you to change one. So we may give you a broken one. That's legit. But you'll know how to do that because you did it, right? Yeah? No, you won't have to memorize all the compilation flags. No. We're much more interested in the dependencies, the dependency chain and how that's handled. Okay, let's see. So the problems of the day, which we have not yet done, we haven't had any days yet apparently, are intended to show you the system by which you're going to download and upload code during these coding exams. Now, we haven't gotten those going yet, but over the next few days, you should see them come live. And what will happen is sometime in the middle of the night while you're sleeping, or I mean programming, oh no, I mean sleeping, while you're sleeping, we will deploy a problem whose intention is to wake you up. My dream, and I don't know if this will ever happen, but my dream is that you'll wake up and you'll kind of stumble around and get some orange juice and a cup of coffee, and you'll sit down at the breakfast table and you'll crunch your cereal and write a little bit of code. And it should take you about that long. I thought about even calling these breakfast tasks or something like that, but that's about the level of commitment we would like you to have to put into them. Now, they're going to vary a lot. Some of them will be like super fast, and some of them will be like, I don't know what they're talking about here and may require a little bit of research. Suffice to say, though, they should only be they should only occupy a small amount of your time in any given day. They're more of an opportunity rather than a stressor. Let's see. What was I going to say? Oh, so those are not live yet, but within the next couple days they will be. And our intention is actually to release a couple of them for you before that first exam, so you have something to practice on. All right. Any administrative questions before I go on? Okay, last time I sort of listed the things that would be on the exam. So I kind of feel embarrassed calling them exams. They're only worth 4% of your grade. So they're not really like exams. They're more like exams. Yeah, 4% each. Yeah. But we have quizzes in lab and, yeah, I don't know. We're not going to do review sessions for them. Life is a review session, right? Yeah, you have to yell. I know, but then that's copying Margaret. Which is, I guess, good. That's the sincerest form of flattery. What? I know it's a good idea. That's right. Okay, we'll call them examlets. At least today in this room. It's a perfect name. Yeah? Quizlets? Oh, you're trying to get me to reduce them. Make them smaller. How about just lets? Okay, let's get to the point here. It's going to be one of those days. Get to the point. Yeah. Okay, so I have declared a variable. Oh, I have declared a variable. Its name is P. Its location is, I don't know. Oh, its location is A40, if that's our representative of memory. Its type is an integer pointer, or a memory address whose value is as an integer. And its value is unknown. It's garbage. It's effectively garbage at this point. The system's going to give you one, you don't know what it is. Give you a memory address, you don't know what it is. All right, so let's work for just a second on giving this thing value. One of the options for giving it value that you saw last time was int x equal 5, and then assigning x to be the, what's the name of the operator I'm going to write here? It's an ampersand, and it means memory address of x. Okay, so if x was set up on the stack like this, and we gave it 5, then P's value here after this assignment is A32. Okay, any question about that? And notice, though, that this is just our representation of what a memory address looks like. It doesn't necessarily look like that at all. Now, this is profoundly uninteresting. In fact, you guys are probably thinking, oh my gosh, do something new. And of course, we've got this thing on the other side of the screen here that we haven't even touched, untouched memory right here. Now, this is heap memory, and the way to think of heap memory is memory whose lifetime you manage. Okay, so heap memory is the lifetime of the memory that you use is managed by the program, which means programmer, you. Okay? In contrast, and we'll see an example of this later, stack memory, the variables in stack memory have a lifetime which is managed by the system. So the lifetime of the variables in stack memory is managed by the system. Okay, and those are two different things, and we'll show you how this works in practice in just a sec. Okay, so now we've got this brand new spanking memory, and we kind of want to use it. And we want to use it in the following way. I'm going to write this command, and of course give you performance art for what it means. When you say new int, you're basically yelling at the system and saying, yo, give me a piece of the heap. New says, give me a piece of the heap. The process by which the heap is managed will give you a memory address, will return a memory address, and that memory address is effectively the right-hand side of this assignment statement. So, for example, if we say P equals new int, there's a little bit of a pause, and we may be given back something here, and that value then becomes P's value. That memory address, that location, name of a location becomes P's value. Okay, any question about that? All right, well, we can now assign to P because we've got this other operator, the value of P, and we can use it to give value to the memory associated with the memory address of P, so which is P's value. I need to draw a picture. What this means is that P is a pointer. When we say new, we carve out space for an integer. The minute we make an assignment, then P points to that integer. And when we dereference P and give value, it's like we walk across the pointer and make the assignment in the corresponding spot. Okay? All right. So that means here in the heap, we've got this sort of picture. This might be just about the last time I draw what's going on in the heap. Okay, I have some questions for you. Can I do this? I'm going to write something, you see if I can do this. Can I do this? String y, P gets the address of y. Could I do that? First of all, could I do string y? What do you think? Oh, what are you asking yourself? What are you asking yourself? Is string a primitive type for C++? The answer is no, it isn't, but it is part of the standard library. So if you declare your intent to use strings, you can treat them exactly as if they are primitive types, okay? Now, they are just a class. You can imagine that a string has wrapped up inside of it some memory that it uses to, keep track of the value of that string. But nonetheless, right now, we're just using it as if it's a class that we know about, okay? All right, so if I say P gets Y's memory address, is that okay? What do you think? Vote, raise your hand, vote yes. Raise your hand, vote no. If I were a little bit faster typer, we'd type it in and see, and when we tried to compile, we would get a type mismatch. So actually, the pointer type goes down to make sure that the way that this thing is declared is correct. Okay, so this is a string, this is the memory address of a string, not the memory address of an int. So the compiler will yell, yell, yell. All right, any question about that? Yeah, Mark? Yeah, okay. So that was actually a point that I wanted to make. I wanted to ask you, what's the name of this memory address right here? What's the name associated with this storage location? There is no name. There is no name associated with it, and that will always be true on the heap. Heap memory is not named except through some variable on the stack. Okay, so you can, if you like, call this thing asterisk P. That would be okay, but it isn't really asterisk P. It's really this thing on the heap that has no name. Okay? All right, yes? I mean, it is asterisk P, but P is the name of the variable, right? And asterisk P means, you can look at it in two ways. P is the name of the variable. That's the thing we're tracking. Asterisk P means take P's value and dereference it. That is, follow the pointer. Okay, so asterisk P means a little bit different than Frog or Jones or whatever you might use to name a variable. Okay, so it's P, but it's an operation on the P. Okay. All right. Any other questions? Yeah? Why is it necessary to declare the type that the pointer is going to refer to? That allows for type checking once you dereference it. So if you weren't careful about that, then if you do dereferencing, then you're going to have type mismatches all over the place. Okay. Yes. If P were a string pointer, yes, that would work. Mm-hmm. Yep. Yes. Okay. I want to keep going. Okay. I'm going to keep going. I think there are lots and lots and lots of questions you could ask here, but I think there's this little sort of multimedia thing that's fun that will answer a lot of your questions pretty directly for you. So I'm going to show you this, and then I have a ton of stuff for us today, so we'll keep going. Hold on. I hope you like it as much as I think you might. And mostly I'm just saying all this to keep talking while I get it set up. Doodle-doo, doodle-doo. You'll like it, I promise. Can you hear? Play.
Hey, Binky, wake up. It's time for pointer fun.
What's that? Learn about pointers? Oh, goody!
Well, to get started, I guess we're going to need a couple pointers.
Okay, this code allocates 2 pointers which can point to integers.
Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything.
That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up is a separate step.
Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee?
Okay, well, this code allocates a new integer pointee, and this part sets x to point to it.
Hey, that looks better. So make it do something.
Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing.
Your magic wand of dereferencing? That's great.
This is what the code looks like. I'll just set up the number and...
Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y.
Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just...
Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it.
Good point.
Yeah, we allocated the pointer y, but we never set it to point to a pointee.
Very observant.
Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x?
Sure, I'll use my magic wand of pointer assignment.
Is that going to be a problem like before?
No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another.
Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over.
Okay, here goes.
Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13.
Yeah, sharing, whatever. So are we going to switch places now?
Oh, look, we're out of time.
But
just remember the 3 pointer rules. Number 1, the basic structure is that you have a pointer, and it points over to a pointee. But the pointer and pointee are separate, and the common error is to set up a pointer, but to forget to give it a pointee. Number 2, pointer dereferencing starts at the pointer and follows its arrow over to access its pointee. As we all know, this only works if there is a pointee, which kind of gets back to rule number 1. Number 3, pointer assignment takes one pointer and changes it to point to the same pointee as another pointer. So after the assignment, the 2 pointers will point to the same pointee. Sometimes that's called sharing. And that's all there is to it, really. Bye-bye now.
Okay. So, one of the reasons I love that so much is that the person who's doing it was the course assistant for my introductory programming class my first introductory programming class in college. He was the a course assistant. So every time I hear his voice, I'm like, oh, cool. And here's the thing, the challenge is actually for you, because it means if you become course assistants in some of your courses, you can do cool stuff like this that will last for decades in the computer science education world, apparently. All right, I don't know who that other guy was. Let's go work. All right, so I think and I could be wrong about this, but at least it was true for me, that the only way to really become facile in the manipulation of pointers was to practice. And so I'm going to I have set up for us just a sequence of assignments, etc., and allocations, and I want us to kind of walk through them, talking aloud and describing what's going on. I'm going to set my other system back up here for a sec, because hold on, be right back. Connecting. Okay. All right. So the very first question I want to ask, based on this code that you see here, is what type of thing is Q? That is, what's Q's type? Every variable has a type, a location, value, and a name. What type is Q? So raise your hand if you if you think it's integer. Raise your hand if you think it's integer pointer. Okay, so probably what we intend by writing this code, it's a little ambiguous, and you'll see why. Probably what we intend is that P and Q are integer pointers, but the fact of the matter is actually that this asterisk applies to only one of the variables. So in this example, Q is an integer type, and if we wanted Q to be a pointer type, our declaration would look like this: int pointer P, pointer Q, okay? Just a little idiosyncrasy and a common bug. So it's the only reason I talk about it. All right, so let's trace through some of this code. This page is intended to be a warm-up. In fact, I'm going to let you spend about a minute and get down to this line. And when you get to that line, put your finger on your nose so I know you're done, okay? So write in your answer on that line, and when you're done, put your finger on your nose. Not in your nose, on your nose. You guys are a tough crowd today. I do not see very many fingers on noses. Put your finger on your nose if you don't want to put your finger on your nose. All right. Here's what I want you to do. I want you to look at the paper of the person sitting next to you. Peek at them, at that line. Raise your hand if their line is blank. If their line is blank. It's okay. I don't know who you're sitting next to. I don't know which way you looked. God, you guys are liars. Okay, fine. Look. Oh, your hand is raised. Your hand is raised. Because you're looking at the person sitting next to you, right? Yeah. One person, this whole line, one person wrote it down. You did? Oh, I'm looking at the wrong line. Okay, I'm embarrassed. All right, fine. I need to go home. All right, so what is output 6? That's right. The picture that I think that even I, at this point, have to draw is pointer P, integer-sized thing called X. P equals the address of X. I dereference P and get the value so that when I print out X, I get 6, okay? What happens when I print out the value of P? Ah, what does it look like? Yeah? Yeah, it's going to give the address of X. Do we know what that looks like? No. If I did it on my machine and you did it on your machine, would it be the same? No, right? So it's kind of meaningless. It's kind of meaningless unless you very deliberately want it for that purpose, like if you're debugging or something like that. So this is a memory address. Okay, so now what I want is I want you to write a simple statement whose output is the value of X, but you cannot use X in your statement. You have to only use P. And what is it? Splat P. Okay, any question about it? Yeah, what's your question? Oh, very good. Okay, this is good. So he says, well, why don't we need heap memory for this? And the answer is because I can grab the memory address from stack variables, right? I can do that always. I can do that anytime I like. The constraint is that why would I ever do that? Because if I really want to be messing with the stuff in that box, I might as well just use X directly, okay? There's nothing here that says I can't always refer to stack memory by their memory address. In a few minutes, we're going to see another reason why we might not want to do that, why it's a little bit dangerous to do that in general. Okay, let's get a little more sophisticated with our examples. I have an integer pointer P and an integer pointer Q, and P is going to get a new int. So right after this line, this is my picture. Okay. Now, Q gets the value of P, means that the data stored in Q's value will be the same as P's value, both of which are a memory address, and the memory address that they are is that memory address, okay, whatever that box is on the heap. Okay. Then I'm going to dereference Q and give value 8, and I think there will be no surprise that when I dereference P and send it to standard out, I get an 8. You like it? So far so good? No big deal? Okay, so now we're down to here. Now I'm going to switch gears a little bit. Say, never mind, we want to do something different with Q. In fact, we want Q to have its own space. Okay, so Q now gets new int. That is, we're reassigning Q's value to be whatever new gives us for this new space. Okay, and then the value of Q equal 9. Happy so far? No surprise, right? Okay. And now we've got this new kind of statement, this unusual kind of thing. We're reassigning the value of P to be what we consider to be the 0 memory address. The way I like to think about it is that we're effectively pulling up this pointer away from wherever it went, and we're pointing it at a particular place. And that particular place happens to be a 0 place, the 0 place, or null. Okay, so now P has value null. Okay, and we can ask it that. We can go, hey P, are you null? And P will tell you whether it is or not. Okay, whereas you can't ask it if it's garbage. Hey P, are you garbage? I don't know. Right? Never garbage. All right. You like this? This is really sad. Yeah? It is. It's pointing, I mean, P points to null, essentially. There's nothing there. It's 0. It's like P becomes 0 no matter what. Okay, this really, really makes me sad. Like, so sad that I want to cry. What's the problem? Yeah? Yeah, right, okay, good. I have to be very collinear, or very careful when more than a few of you have your hands up and I do this. It's not clear like where along that line I'm pointing. So yes, so the issue was, say it again really loud. What happens to the value that P was pointing to? It's so sad. Remember, this was heap memory. It has no name. It has no reference. It's sitting there all alone by itself forever, or until the program ceases execution. Now, that's okay, fine, except if you have a whole bunch of that, all of a sudden you're using up your memory and you have no way to refer to it. This thing, this situation, is called a memory leak. And it occurs when all references to a piece of heap memory are removed. Okay? Now, hold on just a second. So here's the thing. You don't have to worry about this situation on the stack, and I'll tell you why in a minute, or I'll show you the example in a minute. But right now, you should feel like, well, wait, how do I? That is, how do I then say that I'm done with memory? And that's what we're going to talk about next. Did you have a question? What's your question? Sorry. Do I still have Q pointing to it? Do I? No, because Q's pointing somewhere else now, right? Like that was what I did here. The second Q is on the left-hand side of an assignment statement. It's going to point off someplace else, right? So I look around here and I go, oh, there's nothing pointing to 8. There's no way to access it. Okay, so now you may be thinking, wait, I've never had to worry about this before, like in Java, for example. And the deal is that Java's dealing with this for you. Java is watching how you handle memory and going, oh, look, I've got this memory that nobody's referring to. I guess I'll clean it up for you. That's called garbage collection, okay? And there are libraries that will do that for you in C++, but they come at a huge performance cost. So we're not going to deploy them here, and in general, you know, they're fine tools, but they will come at a cost. We just don't need them here very much, because part of what we're learning is how to deal with memory. Okay, any questions about this so far? So now we're in this horrible situation. The question is, how do you remedy it? And the answer is this keyword called delete. So here's what delete does. Delete takes the heap memory location and it puts it back into the list of memory addresses that can be used by new, for example. And that's all it does. Okay, so now when I call delete on Q, it means that this space that we had used for 9 is now available for use by some other function. Okay, any question about that? Yeah? It doesn't clear the memory, that's right. So right, I'm going to say it 85 times. It doesn't clean up the memory at all. It doesn't, like, you know, change this back to whatever you wanted it to be to begin with. And more importantly, it doesn't change Q's value. So at this point, if I said, at this point right here, if I said see out the value of Q, I would probably get 9. Probably, maybe. And I don't know about you, but I don't like it when code is not completely predictable. So anytime we have this probably maybe situation going on, we want to have a remedy. And the remedy here is, once we free up the memory like this, we also pull back the pointer and set the value to null. Okay? So that's what is going on here. Do we like this? Sure. Yes? Do we have to set P and Q equal to null? If we don't, then this statement right here is going to give you indeterminate values. Moreover, you can assign to that spot. So you still have Q with a pointer pointing into some place that's probably none of its business. And that's a little, I want to know what's going on in my memory, okay? All right, any questions about it? Yeah? Yep. Yep. They are connected because this value, the value sitting in Q, that pointer, is still referring to the location of this box. The only thing that happens is that this memory out there might be reassigned to somebody else. I'll show you an example on the next page. All right, any other questions about this? Yeah? Yep, when you delete Q, you're only freeing up that memory for use by somebody else. You have to deal with pulling back the pointer yourself. Yeah, Mark, you got a quick one? Okay. All right, so there's a technical point that's frequently confused, and so I want to take a minute to talk about it. What happens if you delete the keyword there, D, the key D word there is delete a null pointer? It's a no-op. Nothing happens. If your pointer, that's your argument of your delete statement, is null, no big deal. NBD, okay? On the other hand, if you dereference a null pointer, that is, if we said the asterisk P equals new, or I don't know, equals 5 now, and P was null, then we would get a segfault. Because we dereferenced a null pointer. That is, we tried to follow a pointer that didn't go anywhere. That's what happened when Binky fell apart. Okay, there was a pointer that didn't go anywhere. All right, any other questions? Yeah? What if you don't delete Q and the heap gets full? Your program's going to crash, basically. Okay, it'll get an allocation, a memory allocation error. All right, I have one more example. That I hope will bring this home just one more time. Again, I've got P and Q, and P gets a new integer like this, and Q points to P. And then I'm going to, let me give it a value too. I'm going to go ahead and say the value of Q equals, tell me a small integer real quick. Small integer. 1. Okay, the value of Q equals 1. Okay, so now I have a 1 in here. All right, and now I'm going to delete P. I'm going to do this. Probably, if I say C out the value of Q here, I'm going to get 1. That's the probably maybe. But here's what's interesting. That memory doesn't belong to P or Q. In fact, if I write a little bit of code that is something like oh, I don't know, integer pointer R equal new int, and I put a 12 in it. Notice the new syntax that's valid. You can do this. And the system says, okay, you want an integer pointer. Its name is R. You want memory for it? Here's some. Go ahead and use this. Perfectly legitimate. That could happen. No reason for that not to happen at all. And then we assign 12 to it because that's what this statement does. And then we say C out the value of Q. We might get 12. Okay. Now, I don't know about you, but I think I'm done with Q. I might want to reuse it for something else. And all of a sudden, it's changing its value in ways that I didn't predict and didn't anticipate. And sometimes it changes and sometimes it doesn't, depending on the control flow through the program. These are insidious bugs. I think of them as particularly insidious because the bug actually occurred way up here in the code. You can imagine this being separated by lots of computation. The bug actually occurred in one place in the code, but it doesn't show up. It doesn't show up, it doesn't show up, everything's fine, there's a 9 sitting there. It doesn't show up until much, much later. Those things are tough to track down. And you'll get to do those in a lab either this week or next week. I'm not really sure. Yeah? Right, there's no way unless you check it explicitly. And the minute we start talking about checking to make sure it's safe to put stuff there, you're incurring huge computation costs that you don't want to. Okay? All right, any questions about this? Okay. I have a little example here. I want you to take a look at these two pieces of code. And what I want to know is if and how they differ in functionality. Okay, so if you compiled these and watched these execute, what would happen? Compile them and you watch them execute. Are they the same? What's the output of the one on the left? What happens when you compile and execute the code on the left? What is output? Can I trace this? Really? What is output? Hello, very good. If you compile and execute the code on the right, what do you get? Hello? Yeah, so they're very nearly the same. There's a greeting from each one of them, right? Each one of them gives you a greeting. The one on the left is much more aggressive and confident. The one on the right, it's a little timid, hello. But as you can see, there are different things going on in memory in each of the cases. So even though their execution is really not very different from the client's perspective, what's going on behind the scenes with memory is significantly different. So I want to talk through this. Well, I'll ask you a couple questions about them. So program flow in main calls the function fun and returns back. Inside the function fun, we have this variable s. And inside the function fun in the other example, we have this pointer. Okay? Now, my question for you is, where does this live? Where does this one live? Yeah, very good. And where does the local variable live in this example? Wrong. Oh, okay. So here's what's going on. Remember, all of the variables are on the stack, right? All the variables are on the stack. So when you execute this function, there is this area of memory, S, and actually all local variables and all parameters are set up in the stack. It gets the value hello in its memory and the memory associated with S. It's printed out, hello, and then program control passes back to the calling function. At that moment, S is cleared off the stack for you by the system. That is, the lifetime of S on the stack was determined by its presence in the function, its scope in the function, and it was administered via the stack. Okay? So when I say a variable's lifetime is controlled by the system, that's exactly what I mean. Any question about that? Okay, let's trace that. That's using that same dialogue. Let's trace the other piece of code. So we call function fun, which means program control passes to this function. It sets up a variable on the stack. I guess I'll make us a new stack. Its name is still S, and it's a pointer type. We say new string, and somewhere else, you know, a spot that contains string is given to us. The value of that string becomes hello. We can dereference it and send it to standard out. This works fine in C++. Then we can delete S, that is, say I'm no longer going to use that memory, and then program control passes back and S is removed from the stack. Okay, any question about that? I have all kinds of questions for you. So if you want me to take over control of the conversation, I'm happy to do so. My first question is, which of those is faster? The one on the left, absolutely. Even though we don't know what strings do, even though strings might allocate dynamic memory in their constructor. In fact, they probably do. But suffice to say, we're saving ourselves a memory allocation on the heap together with a couple dereferences. So we're quite happy keeping things as fast as possible and using this one. So prefer stack variables if you can do it. I have another question for you, and that is, what if I do this? What if I get rid of delete S and I execute this code? How do you feel about that? What do you think? Is that okay? Yeah? Yeah, it's a memory leak, right? My only handle on that new memory that I asked for was S. And S goes away by the scoping mechanism. The S goes away as soon as program control passes out of the function. So the second we pass back, hello is still sitting out there alone, a voice in the wilderness by itself. Okay? So that's why we have to delete it. All right, any other questions? Do you have questions about this? All right, yeah? Is what? So the question is about the pointer and the pointee, okay? So what happens with this delete statement? Remember that delete actually has an action on the pointee, the thing that's pointed to. It sends that memory address back for reuse, okay? So the second I say delete S, this memory address is given back to the system, okay? S still has that same value. That is, S still refers to that, but it promptly goes out of scope, so we don't care anymore. You could, if you want to, say S equal null here, but you don't have to because S is going to be gone. Okay? All right, we'll see more examples. We'll see a ton more examples of this. All right. Bye.
I took the CS275.
I'm working on it. They're not graded yet, but they will be very soon.
Thank you.
Sorry.
I have a question about MP1.
Yeah?
Do we have to use pointers in MP1?
Yeah, you do.
Can you do it without it? I mean, the way I did it was just to copy the values.
Oh, you reallocated a new... I think that's fine. I don't think any of our test cases look at your memory profile, so I think it doesn't matter.
Okay.
I think that's true.
Oh, was that if at the point to the pointee, but the hello is deleted, so the item point is not there.
So yeah, but then S is removed from the stack by the scope. As soon as, so it's the same thing as over here. As soon as you pass program control back, that is as soon as you get to the end of this function, all of its variables are cleared from the stack.
Also, as is clear, so why should we delete it?
Because its pointer is not freed. It's the thing it points to is not freed. Only S itself
Only
is
as is deleted, but the pointer is still now.
right. So you have to do both because S is kind of this mixture, right? It's a variable on the stack, but it points to deep memory.
But only if I don't delete the as after the program.
If you don't delete S, then there's a memory leak. If you get rid of this line, then there's a memory leak because you send control back and this hello has nothing pointing to it. Does that make sense?
The P, shouldn't the P also be
No, that's the value of P. Remember, look over here. So P has a memory address as its value, right? If you dereference P, then you go to that memory address and you get the value.
Yeah.
Okay, but we didn't do that here. We just said see out the value of P. The value of P is this one, each one.
Oh.
You should go try it yourself. You should go write this code and see what it does. Go put this in a main and see what it does. Okay? Yep. Because you'll ask yourself a million questions. I'm going to step right out here.
Will there be iClicker today? Oh, okay.
Oh, yeah, there will be iClicker
Question.
Okay, thank you.
Do I feel this part is
Yeah,
like
so
just one more? I think it's one more.
so just click this.